So, I'm Jannik Laval, PhD student from Hermod team, based in Lille, and since 1 year. So I will present today how to detect system cycles with DSM, and it takes 30 minutes. So DSM is Dependency Structure Matrix. So it's a matrix based on dependency, and it allows us to organize tasks based on their dependencies. So the roadmap is, first I will present what is a cycle. Then I will present what is DSM, and after I introduce in DSM some colors and some other information, and I will present DSM applied to C-site 2.9 and to all packages of FAO. And finally, I present some works that we do in research. So what is a cycle? A cycle is a path which comes back to its origin. It's between two or more elements. For example, here, between A and B, there is a dependency from A to B and from B to A. We have a cycle. And we talk about a direct cycle. A direct cycle is between two elements. There is another direct cycle between C and D. And if there are more elements than two, like between A, B, and A, C, and B, we talk about an indirect cycle. So this is a graph, okay, and we talk about after on DSM. So cycle between packages make questions. Yes. I talk about cycles between packages, not between classes, between packages. Okay? And it makes questions about dependency logic, about the modularity, and how to build dependency. Now, if you want to see cycle, to see dependency, okay, we can say graph, okay, it's a graph. It's a graph from C-site 2.9, okay, it's horrible to see dependency. There is no cycle here, but we don't know, okay. Now, what is DSM? DSM has for origin process optimization, and it is used to organize tasks by dependency. So, and now it has been applied to dependency in software reengineering, and DSM, so it's like this matrix. It's compact, and it allows us to structure the visualization. So, and it supports cycles and layer identification. So I talk about layer after. Now, how can we make dependency matrix? So here we have a dependency between C and D, in the DSM, at the column C and the row B, we make a cross. Or if we want the adjacency matrix, we make a 1, the number 1. We can do this with weighted number. We can see this after. So, DSM is each cell in the DSM represents a dependency. If there is number in a DSM, there is a dependency. If there is no number of 0, there is no dependency. A column represents the package used by the header. For example, the first column represents the dependency of package A, and A depends on B and C. And a line represents using packages. So, for example, the line C is used by A and B. We can see easily some cycle, a direct cycle, because of the symmetry. Yes? The number, this is random number, but we can put cross 1 or weighted number, for example, to express hierarchical dependency or invocations.
In fact, the strength of the dependency. If you have any reference from D to C, or 1 from C to D.
So, okay. Between C and D, we see a cycle because of the symmetry by the diagonal. And direct cycle is easily seen. So now the number. The number in package, in DSM applied to package, can represent inheritance, direct class references, invocations, or extension. So everybody knows extensions. Yes, so I don't explain what is it, but in our case, we used to reverse dependencies. If I have a cycle, I can use extension to reduce cycle. Now, how can we detect cycles? There were two methods. One named squared adjacency matrix, and one which is the path searching. So the squared adjacency matrix, okay, we have a graph. We make a matrix. We make the adjacency matrix with 0 and 1, and we square this matrix to have another matrix, and in each cell in diagonal where is non-zero value, there is a cycle. Here, G, H, and E are indirect cycle. So G and H and E. If we square another time, we detect cycles on level 3 and 4 etc. This technique has the advantage of this is mathematical approach, but we can't distinguish. Thanks. We can distinguish cycles. For example, this matrix, there are two cycles between A and B and between C and D. If we square this matrix, there is one on all the diagonal, but we can know by this method if A is in cycle with B or C or D. The second method, which is the path searching, so it is easy. First we use the path. Here we have a direct cycle, another direct cycle, and we have indirect cycle in between F, H, and A, G, and K. Okay. So the path searching has the advantage that we have information about path, but it is slower than the first approach. Now, come back to the DSM. Here is the DSM of package of all the package network of Faro. So, what do we see? A cycle, another cycle, okay, direct cycle, there is a symmetric, another cycle, there is another cycle, okay. Here, there is a column package which uses a lot of other packages, but this package is never used. Okay? So this package is network test. Okay. Network test is used by no package, but use normally all other packages. We can see here another package which is used by some other packages, but use no package. This is something like a core package. Okay, what about cycle now? When we have cycle, we can merge them and consider them as a single package. So here we come back to the network matrix. We have a big cycle. So I show you this later, but this is a big cycle. We merge all these packages in one, and we have a matrix without cycle. And with this, we can do layer. So the first layer, 9 and 10, which use no other packages, but is used by the other packages. There are core packages. Okay. Then in layer 2 we have the package 3 plus, and in layer 3 package 1 and 2. The method of merging is used for layer. Okay. We can use it for that. So, okay, DSM allow us to spot cycles, to identify layers, And now, okay, now we have programs to read cycle, to read dependency, and we don't know how and where to fix those dependencies. So we can use colors. Here we can use red for direct cycle, yellow for indirect cycle, and pale blue for complex cycle. When we talk about complex cycle, is a lot of cycles in a lot of cycles which are imbricated. And we would like another thing is I don't want one number but 4 numbers. I would like a number for inheritance, another for direct class references, another for invocation, and another for extension. Okay, we came back on the example network. This is the first matrix. This is the second matrix with colors. Okay. What we see here, we have a cell with some numbers, T for total, R for direct cycle, direct class references. There are S for invocations. Okay. Now we can see the cycle because there are red and pink. We have another cycle here and a complex cycle. This is the complex cycle that I have merged before. Because all of these packages are in cycle. And we offer prognostic. In these cycles, the red cell represents 8 dependencies. Okay? And the pink one represents 71 dependency. So if we want to remove this cycle, it seems to be easier to begin with the red cell. Okay. Now, the program, with this color, we can do, we have a dissymmetric cycle. Okay, maybe we can remove this cycle or reverse links with, for example, with extension, or maybe we can do other things. If we have a symmetric cycle, maybe we can merge these 2 packages, or make 2 different packages, reorder classes, or maybe other things. Okay, DSM at work. I will present C-side 2.9. There is no cycle. And for. Okay, C-side 2.9. This is the graph. It's horrible. This is the matrix. Okay, package core is here because it is used by all other packages. Now, for this is a graph. Okay? This is the DSM. Okay, the small square in the center is mousse. it is fixed now. And the square in blue part here represent the core of FAO. So all the system packages, FAO or Squeak. Okay. They represent system packages, Morphic, a lot of things. Okay. So it's but in DSM we can see more things than the graph. Now, what we can do more, so in research, for example, in each cell, we put some other information. This square represents a cell, and we put on it a class involved in a cycle. We use color, blue for inheritance, red for direct accesses, green for invocations, and black for extension. Okay. There are some other color and convention, but it's not important for this presentation. This is an example of a cell. Okay. And here, an example of a cycle. We have the white cell and the pink cell. Okay, the white cell. Before I say that the white cell is easier to fix, here we see that it seems to be easier to fix because the pink cell is complex. There are edges. Okay, lots of edge. So, we come back to the package network. Okay, we have this matrix, and if I take only the complex cycle, we have something like this. Okay, we can see that some dependencies are complex and some easy. So, I have finished. Okay. So, DSM. We can use them for classified dependencies, to detect cycles, to offer prognostic with pink and red cell. And there are two tools to do this. There are lattice, and I propose the website, and you can download eDSM, which I've made in our team. In the website of NOS.
Wait, just something that maybe wasn't really clear from the beginning of the talk. The idea is that we did not want it to make a research presentation, because else we would focus on the last bullet. What we wanted to show to the community is that if you have dependency between your packages, this is an easy way to build your own small programs that you can manage a bit your math in your system. And like that you understand, okay, with the matrix we can do that, and the algorithm to compute. This is just the matrix square or looking for that. That was the intention of the presentation.
Yes. Are we going to the invocation dependencies? Do you have that information in small part? Is it on a runtime or?
This is made by files.
This is static. So
matrix for what a good package structure is and are there any optimization algorithms for that?
You mean in the DSM?
Yeah.
No, the DSM, this is really a way to describe tasks in organization processes.
Yeah.
So after what you put inside, this is what the dependency that you want for your task. Then after what you are asking, this is are metrics, for example, software metrics that would qualify a package as better than another one. And to that regard, you have two kinds of families of metrics. You have the matrix that says the package is well defined if this is cohesive and loosely coupled with the rest of the system. And somehow that can be good, sometimes not. And you have also metrics that says if all my clients use me or use the same part of me, then I have a good package. Because maybe inside I am loosely coupled and I'm not referencing too much, but my client, they really see me in the same way. So yes, in the literature I will define some metrics for that, but this is not applied to that. There we only focus on the dependency.
Have you looked at Travis Spriggs' browser dependency tool? He has a way of classifying dependencies that might be of interest to you.
Okay, thanks.
I'll happily show it to you.
Yeah,
Come up as soon as there's a break. I'll show it to you.
In ESUG there is a dependency package browser that we look at.
In the matrix, when you did DSM by squaring the matrix, you mentioned that you produce blurry cycles because now you know all this once and what is happening. What happens if you start squaring? Let's say that you find that packages A, B, and C are connected to each other, but you don't know how, and you rerun that by taking out A and seeing if B and C are still connected in the absence of A. Can that be done? Is that feasible, or it doesn't know? I don't have to do n squares. It's still going on.
How long does this take to compute? For the packages on Faro, maybe 3-4 minutes. The problem is to import Faro in Moose. It takes several hours. But the DSM in 3-4 minutes.
But if you have a small talk application, you don't have to create the meta model, it's there.
Yeah.
Because in Moose, what we are doing, we parse all the code, we analyze all the code, we produce entities, because we want to be language independent, so like that we can load Java, C++, and all other languages. So now if I do I think that in a company that has a small code base, I think that you probably will just directly use the senders, implementers, or reference, and it should be much, much faster.
3 minutes or 3 hours?
3 hours. Because the 3 minutes, once you have the data, this is just the computation of the matrix. And how many packages are in Faro?
150.
150 packages. So that's not a toy. And this is full of mess, so no, but in a modular system, you will go faster because you have less cycle anyway. So
If you know you have dependencies, are there tools that can fix it for you, that can merge packages together, for instance, or change superclasses? Or is just an analysis tool and not?
For now, this is an analysis tool. We worked on